Hello to all physics enthusiasts and experiment lovers. This is Andrei Shchetnikov with you. Finally. Alexei and I have gathered to shoot a big video about the emergence of lift force in a wing. To understand how this force arises, to resolve various debates surrounding this topic, to analyze paradoxes, and we will start with a very simple dispute. When some say that the lift force of a wing arises because the wing has an asymmetric profile, being more curved on top than on the bottom, others argue that no, the cause of lift is the presence of an angle of attack. Well, we will answer this question with a simple experiment. For this purpose, we have assembled a rough imitation of a wind tunnel. Air from the blower will flow around the profile mounted on this frame. And now the profile is chosen to be symmetrical. The frame itself is placed on a force sensor. I will reset it at the beginning of the experiment. Then I will set the profile at a certain angle of attack, blow air over it, and measure the lift force that arises. And here are the results of the conducted experiment. The angle of attack varied from -30 to +30 degrees. Within this range, the lift force was proportional to the angle of attack. But this time we will use an asymmetric profile that is strongly curved on top. The experimental points again fall on a straight line, but this line is shifted upward compared to the line from the previous experiment. So even at a zero angle of attack, the asymmetric profile experienced a lift force of 50 minas. The conclusion from this is very simple. Lift force is created both by the positive angle of attack and by the curvature of the profile. And there is no point in opposing one to the other. On aerobatic aircraft, which spend a significant part of the flight upside down, there is no point in making the profile convex on one side. In this position, it will only hinder the creation of lift force. So here the profile is symmetric, and all the lift force is created due to the positive angle of attack. And on large airliners, which will not fly in such a position, lift force is significantly created due to the curvature of the profile. Although a positive angle of attack is also present here. The next debate that often occurs among aviation enthusiasts goes like this. Lift force arises due to Bernoulli's principle, some say. The upper and lower sides of the wing are streamlined at different speeds. On the upper side, the speed is greater, so the pressure is lower, and it is this pressure difference that creates lift force. No, others say, lift arises from the action of Newton's third law. The wing deflects air downward, and due to this change in momentum, a force acts on the wing upward. Well, this debate is also meaningless because one is impossible without the other. This is simply two sides of the same phenomenon. And the debaters behave like those who argued about the appearance of an elephant in the dark. The change in momentum of the airflow can be demonstrated with a very simple experiment by attaching threads to the trailing edge of the wing. At zero angle of attack, the flow behind the wing still deflects slightly downward. And if the angle of attack is increased, the angle of deflection of the flow becomes quite significant. To demonstrate how the pressure difference arises on both sides of the wing, we had to build this setup, a kind of small wind tunnel, in which the blower will work by sucking in air, and the air will enter and flow around the profile inside the tube. Two copper tubes are connected to the two surfaces of this profile. They descend downwards and are connected to two elbows of a U-shaped manometer. We turn on the blower, and a difference in levels of 3 centimeters is established in the elbows of the manometer. This means that the air pressure on the convex surface of the wing is lower by 300 pascals. And although our wind tunnel is quite primitive, it demonstrated everything we need. Now we will talk about how the pressure difference arises on the lower and upper surfaces of an asymmetric profile. For now, settling for a simple school explanation and not delving into various nuances. Well, we start with the formulation of Bernoulli's principle, which states that in a steady flow along streamlines or along flow tubes, a certain quantity is conserved. the sum of the dynamic pressure, RV22, and the pressure. Well, accordingly, let's now look at the flow that hits the wing. The upper flow tube is somewhat constricted by the wing. Its cross-section becomes smaller than that of the lower tube. But since the cross-section is smaller, the speed is greater. And according to Bernoulli's principle, if the speed is greater, then the pressure is lower. Thus, it turns out that the pressure on the upper surface of the wing is lower than on the lower surface. By the way, we just observed this in the experiment. And this slight difference in pressure creates an upward lift force. Now I want to return to the various judgments that arise in discussions on the internet. For example, among them is this one. Some people believe that the flow speed above the airfoil is greater than below because two air particles arriving at the leading edge and one going along the upper surface while the other along the lower must reach the trailing edge at the same time, and the path above is longer. But this judgment is not correct. Let's take a look at the video taken in the Cambridge University wind tunnel. The airflow is periodically highlighted with short smoke pulses. It is clearly visible that the flow under the wing noticeably lags behind the flow above the wing. They do not arrive at the trailing edge at the same time. Another reasoning I have encountered looks like this. Let's consider a wing whose profile is a thin arc. Such wings were made in the dawn of aviation. Well, it seems that when air flows around such a wing, it will move above and below at the same speed. Where then will the lift come from? However, this reasoning is not correct. Because if we look at the stream tubes, again, the stream tube above such a profile is constricted, while the stream tube below the profile is forced to expand. Therefore, from the principle of continuity, it follows that the speed above is greater than below. Well, again, we come to the conclusion that the pressure above is less than below. And by the way, we have another reasoning that shows that the pressure on the upper surface of the wing must be noticeably less than the atmospheric pressure in this area. Let's look at a particle that moves along this line. This motion is not linear. The particle changes the direction of its velocity, which means a force is acting on it that makes it turn, and this force is directed towards the wing. What could cause this force? Well, only the pressure difference on one side of the particle and the other. Here it is higher than here. Therefore, the pressure decreases in the direction from areas far from the wing directly to the wing itself. Here it is lower than atmospheric pressure. So far, I have discussed such misconceptions that seemed quite trivial to me. And now I will move on to a misconception that I myself held for quite a long time, and it is related to how streamlines are drawn. We can see a picture where the air flows horizontally towards the wing, then flows around it, and behind the wing, it goes down in accordance with Newton's third law, as it should. And then it turns out that there is such a line, which I will depict here horizontally, and then it drops significantly down relative to this level. This drawing leads to a contradiction. In fact, I will reduce this drawing, continue the highlighted streamline on both sides of the wing, and draw two more streamlines far above the wing and below the wing. They will be practically undisturbed and thus straight. Moreover, I will draw them so that in front of the wing they are equidistant from the center line of the flow. And now I will consider two airflows that flow above and below the center line. In the undisturbed zone in front of the wing, they move at equal speeds. But behind the wing, the cross-section of the upper flow will be larger, while the lower flow will be smaller, meaning the lower flow will move on average at a greater speed. But this should not be the case, as we assume that far from the wing all disturbances disappear, and the flow from all sides should be undisturbed. The solution to this contradiction is that the center line of the flow must not only go down behind the trailing edge, but also rise up in front of the leading edge of the wing. And the correct drawing would be like this. This means that the momentum of the airflow in front of the wing is already directed partly upward, just as behind the wing it is directed partly downward.
And lift is essentially the reaction to such a change in momentum in the system. But how does the air in front of the wing know that it needs to rise? You might wonder. The answer is quite simple. The point is that we are considering significantly subsonic flight speeds and, accordingly, subsonic airflow speeds relative to the wing. And this means that the corresponding disturbances spread from the wing both forward and make the air move as needed. Well, in addition, it should be noted that we are considering a wing with a very high aspect ratio, assuming that the flight speed is constant and making various assumptions. And here I suppose I have figured out all the initial paradoxes that I wanted to understand. And I am ready to pass the word to Alexei for a discussion on the theory of lift generation for wings proposed by Zhukovsky.
But I will start not with Zhukovsky's model, but with the paradox established by the French encyclopedist Jean-Laurent d'Alembert in the mid-18th century. This paradox is as follows. Let's imagine a sufficiently streamlined body that moves at a constant speed in an incompressible and non-viscous fluid, or what is the same, an infinite flow of fluid moving at a constant speed rushes against a stationary body. And it turns out that the sum of all pressure forces acting on the body from the fluid is exactly zero. And this means that the drag force directed along the flow will be equal to zero, and the lift force directed perpendicular to the flow will also be equal to zero. As the first example, let us consider. We will review the inviscid flow around a cylinder. In front of the cylinder, the flow is decelerated, and according to Bernoulli's principle, a zone of increased pressure is formed here. On the sides of the cylinder, the stream tubes are constricted, the flow speed increases, and the pressure drops. But the most interesting thing happens behind it during such flow. The flow speed here is low, which means the pressure is again elevated. The pressure distribution turned out to be symmetrical, and therefore the total aerodynamic force is equal to zero. And although the flow pattern constructed within this model looks quite convincing, in reality, we know that the flow around the cylinder occurs with drag. The thing is that at sufficiently high speeds, the flow behind the cylinder separates, creating a turbulent zone, so the flow is definitely not symmetrical. Now let's look at the flow around a thin, arc-shaped profile. And we unexpectedly see not only a low-pressure zone above the wing, but also two areas of low pressure under the wing edges. And the high-pressure zones are also located not only under the wing, but also above the wing edges. And as a result, the lift force of such a profile in this model is again equal to zero. And now let's look at a standard profile. Above it, of course, a low-pressure zone forms, but the pressure also decreases below the trailing edge and increases above it. Why does this happen? The thing is that in this mathematical model, the streamline separating the airflow below and above the wing does not originate from the trailing edge of the wing, but from a point that is located on the upper surface of the wing. And at this point, the airspeed is obviously zero, while the pressure is at its maximum. Here, a zone of increased pressure is formed. And now let's look at the streamline that is forced to bend around the trailing edge of the wing. Here, the air sharply turns, and this can only happen because the pressure is significantly lowered here. But it is clear that this is only a mathematical model, and physically, the streamline that separates the flows above and below the wing should originate from the trailing edge of the wing. Here, we transition to Zhukovsky's model. Nikolai Yegorovich Zhukovsky was not an aircraft designer, yet he is called the father of Russian aviation because he developed the wing theory, built the first wind tunnel, and established the Central Aerohydrodynamic Institute, TSAGI. And to understand Zhukovsky's theory, we need to recall two conditions once again. The streamline must originate from the trailing edge of the wing. And we also need to remember what Andrei said. The streamline approaching from the front must rise from below. And to clarify these requirements, we will now conduct an experiment. With this simple glider made from two glued cups, we launch the glider using rubber twisted around it. It ascends and descends along an inclined trajectory. Let's slow down this video and do a tracing. The descent occurs at a constant speed, which means the aerodynamic force exactly balances the force of gravity. At a speed of 480 frames per second, we can clearly see the rapid rotation of the glider, and it is this that generates lift. When the cylinder rotates, it draws the surrounding air into this rotation. And if we now overlay a uniform airflow onto this circulation, then the speeds add up above the cylinder and subtract below it. And now it turns out that the cylinder is surrounded from above by a flow with a higher speed than from below. And in the model of an ideal fluid, the flow pattern looks like this. Here, an upward streamline appears in front of the cylinder and a downward one behind it, which we have already mentioned several times. And according to Bernoulli's principle, the flow speed above the cylinder is greater, which means the pressure is lower than below the cylinder. As a result, an upward directed lift force acts on the cylinder.
Lesha, probably many of our viewers have already wondered why we depict minimum pressure in red and maximum pressure in green, even though it seems natural to use this color scale the other way around.
The thing is, for drawing the airflow, we use a program designed for calculating magnetic fields. And actually, this picture of a cylindrical superconductor with current flowing through it in an external uniform magnetic field. Hey, is that possible? Of course it's possible, because the mathematical equations describing the airflow around the cylinder and the magnetic field are completely identical.
And why did the colors change?
And this is important. The thing is, instead of speed, we are actually depicting the magnetic field. Where the magnetic field is maximum, the pressure of the magnetic field is also maximum. And during the airflow, where the speed is maximum, the pressure is minimal. So everything turns out to be the opposite.
Well, then there is a natural second question. We are currently considering the airflow around a cylinder, but our video is actually about the airflow around a wing. How do the two relate to each other?
Well, here we transition to Zhukovsky's contributions, who, using the advanced methods of complex variable theory at that time, obtained the familiar wing profile from a circular cylinder through conformal transformations. Zhukovsky's genius lies in the fact that he used a very simple complex function z plus 1 over z. This function transforms the unit circle, shown in blue, into a red segment. If the radius of the circle is changed, the segment will turn into an ellipse. And if the center of the circle is slightly shifted, with the right choice of this shift, the ellipse transforms into a curve very similar to the profile of an airplane wing. As a result of these mathematical transformations by Zhukovsky, and subsequently by us in the Vizimak program, we obtained this picture, where the streamlines leave the trailing edge, and the added circulation creates lift.
And yet, what has been said now, is it pure mathematics? Or is air really circulating around the airplane wing?
Zhukovsky discovered circulation at the tip of a pen, but we can indeed observe these vortices under certain conditions. To understand how this is possible, let's depict the attached vortices around the wing. Now, let's consider that a real wing has a finite span. The pressure under the wing is greater than above the wing, and air at the tips of the wing flows from the lower surface to the upper, forming tip vortices. These vortices are shed by the oncoming flow, resulting in a wake behind the wingtips consisting of two vortices rotating in opposite directions. And these vortices can be seen when the airplane flies through the edge of a cloud or lands in a strip of fog. Moreover, the presence of airflow circulation around the wing allows measuring lift force without using aerodynamic scales by the half-ceiling method. To do this, the speed is measured at the top and bottom of the wind tunnel, then circulation is found as an integral of speed over a closed contour, then the aerodynamic force is calculated using Zhukovsky's formula.
Okay, I understand. You have convinced me of the existence of circulation around the wing, but the question is, what determines the magnitude of this circulation, and where does this circulation come from in general? Because it is the magnitude that will ultimately determine, according to Zhukovsky's formula, the lift of the wing for a given profile, angle of attack, and flow velocity.
Well, based on the mathematical model, it is very easy to answer this question. Because for us to have good flow around the wing, the streamlines need to leave the trailing edge, as we have already discussed. And this condition unambiguously determines the magnitude of circulation. From this condition, which is also called the Kutta-Zhukovsky condition, we define it.
Okay, but this is mathematics. How does the airplane or wing know that the circulation should be exactly this way? How does it arise? After all, at the start we had no circulation. There are theorems by Helmholtz about the existence of vortices, stating that if there was no vortex at the beginning, there won't be one later. Where does this twisting of the flow around the wing come from?
Well, it should be noted that we have been discussing the model of an incompressible and non-viscous fluid. Well, all these vortices must obviously be generated by some viscous forces. This requires complicating the model, but I wouldn't take that on.
Okay, I understand. And it seems to me that in that video from Cambridge, we can show how all this arises. To try in any case, the flow around at this angle of attack is still occurring without separation. But let's look at the trailing edge of the wing. It is clear that the flow behind it is not smooth. There is a constant generation of vortices. They are carried away by the flow, but they appear again and again. And the flow is subsonic. Therefore, these vortices determine the structure of the flow not only behind the wing, but also in front of it and from all sides. And that means they are the ones creating circulation around the wing, because there are no other reasons for it.
And here we can continue to ask questions about these vortices. What instabilities generate them? What is the role of forces, viscosity, etc.? And we can delve infinitely deep. But we will not do that here. Instead, we will move on to our traditional concluding question. When the airplane lands in wet weather, one can observe how trailing vortices detach from its wing. But they are formed not at the ends of the wing but at the ends of the flaps. Try to explain why this happens. Please share your thoughts on this in the comments of this video on YouTube.